right, so imagine that I have a user that's connected is at an Orlando, Florida branch. And this branch has an IPsec tunnel that's configured to a Zscaler or an Axis, an SSE that's in Dallas, Texas. Now, what will happen is if the user, let's say the user wants to connect to sp-ipsla.silverpeak.cloud. When the user goes to resolve sp-ipsla.silverpeak.cloud, it's very important which way the DNS queries go. Because if the DNS queries break out locally, like if you have your EdgeConnect configured to break out 8888 to local breakout, that means that the DNS queries are going to hit a local name server, like in Orlando. It will anycast to the closest 8888, and that local Orlando or Central Florida-based 8888 is going to respond with the closest IP for sp-ipsla.silverpeak.cloud. This is very common method on the internet. This is where you, depending on where you are, when you do a DNS query, you'll get whatever IP address back in the DNS query that's closest to that name server. This happens all the time across the internet, everywhere. The problem this presents is if I do the DNS query and I query a name server in Orlando, but then my overlay policy tells me to route that traffic across a SSE tunnel, well, look what's going to happen. So I'm going to get all the way to Dallas. I'm going to then turn around and come back to Orlando because the DNS query was sourced from Orlando, but the socket itself, the actual flow, went all the way to Dallas, only to turn all the way around, come back to Orlando, go back to the Dallas NAT point for the SSE provider, and then back across the tunnel. This is horribly inefficient. So the EdgeConnect solves this in the way that you might be able to imagine. When we do a synthetic ping, or when the user goes to resolve a host name for an IP for an AppExpress domain, we will intercept that DNS query, send it the same path that we expect the user's subsequent TCP connections to go. We'll send it across the tunnel. That means now the DNS query emerges onto the internet from Dallas. That means it's going to get a Dallas IP address, or it's going to get the IP address for a data center that's in Texas, not in Orlando. So now it's like a couple of milliseconds from here to here, and we don't have to circle all the way back around. So now after that, the user then will connect to an IP address that's like 4 milliseconds away from the front door of that SSE. We respond back and it comes back again. So there's no tromboning, there's no paperclip routing that occurs here. This optimization is incredibly important because if you're polling across, if you're resolving IPs one way and polling the other, you will not get the right answer with regard to the proper path from a performance standpoint. It's important, and it's a tricky problem to solve. And the way that we solve it is through the use of the DNS proxy. Now, we've changed the DNS proxy with AppExpress. It now has 4 automatic modes that it can exist in. So first of all, there's a disabled mode. That means that's AppExpress is not running for that application or at all, and you are not using the traditional column AB mode. You'll see default mode is the current DNS proxy mechanism, where you have, you see over here, you have a DNS server A, a B, and you send everything to this, and whatever's left over you send to that. That's still supported, and that will show up as deployment mode default. But now there's another mode called AppExpress only. So let's say you've never even heard of the DNS proxy. When you enable AppExpress, it will turn on the proxy just for the app that you have configured in AppExpress. All the other DNS queries will pass through without even being touched by the DNS proxy. And then there's hybrid mode, in which we use both AppExpress and the AB configuration at the same time.